All right, so we're looking here at Pauli's problems. This is actually 7.7, so I'm just going to kind of put that here. Notes. And it says, we've been helping Mrs. Gallus's neighbor, fourth grade Polly, and Polly has an older brother whose name is also Polly, but it's spelled differently. He's learning about solving equations in his Algebra 1 class, so let's help him with his homework before we start our lesson. So the first thing it says is Paulie needs to do these two problems for his homework. Solve each problem for X, show your work, and explain how you got your answer so that Paulie would understand. So I'm going to look at the first one and try it yourself, but there's many ways to do these. But the first one, I'm just going to do it very algebraically, add 100 to each side, and then I get 2x squared equals 100. And then just divide both sides by 2. Then I get x squared equals 50. And then to get rid of that square root, or to get rid of the squaring, I have to do square root, but what I do to one side, I do to the other. So I get x equals, and when I take square root, I get two answers. So I get plus or minus the square root of 50. Or if you wanted to, you can always break that down a little bit more and call it the square root of 25 times the square root of 2, which would really be 5 times the square root of 2. But this will work. We can leave it like that, or you could write it this way too. So that would be doing the first one. So we get two answers, 5 times the square root of 2 and negative 5 times the square root of 2. And then we're going to go look at this other one. In this one, I see it's a quadratic, and I have a couple of choices. I could try to factor it, but we'll find out that it probably doesn't factor. So I'm talking about doing the box here. I do x squared and then 16. And then I would do a little diamond problem here. We haven't done this for a while. And I'd have to say, all right, it needs to multiply to 16, but then add to 4. So I'm looking for two numbers here that add to 4 but multiply to 16. And to get 16 positive, I'd have 1 and 16, 2 and 8, sorry, 2 and 8, and 4 and 4. But none of those combinations will add up to positive 4. So that means I can't do anything. It means that it's not factorable. But it doesn't mean I can't get an answer. So because none of those combinations that are possible work, I'm going to have to use another method. So I have two methods, and the methods that I have are I could use quadratic formula, and that's where I have that negative b plus or minus square root of b squared minus 4ac over 2a, and that will give me what I need for x. Or I could do complete the square. Now, both methods will give me an answer that will be the same. And I'm going to use complete the square, but you could do it with quadratic. So complete the square, I'm going to subtract 16 first from both sides. And when I do that, I get negative 16 equals x squared plus 4x. Now, I need to add something on here to complete it to make it a perfect square. What I do to one side, I'm going to have to do to the other. So I'm going to start with a box for complete the square, except this time I'm going to put x squared here, and then this part is going to be part of the middle. So I'm going to split that 4x up perfectly into 2x times 2x. Now why I'm doing that is because I want the two sides here to be exactly the same, so it makes a perfect square. And this way it will, because I'd have x plus 2 and x plus 2 But there's this other little part that's right in here, and that's the part that I'm going to use to complete the square. And that's really going to be what 2 times 2 is, and that's 4. So to complete the square, I have to add an additional just number 4. But what I do to one side, I got to do it to the other. And when I do that, now instead of writing it as this whole piece here, which is this, this, and this, I can just call it x plus 2 times x plus 2, or call it x plus 2 squared. But then on this side, when I add these two together, I get negative 12. And then I can take the square root to get rid of that square. And I get x plus 2. Then I have a problem here because the square root of a negative is going to have an imaginary part to it. So I'm going to kind of break up this square root of negative 12 into the square root of 4 times the square root of 3 times the square root of negative 1. Or I could write it as the square root of 4 times the square root of 3 times the square root of negative 1 equals x plus 2. When I do that, the square root of 4, that's a nice number. That's just 2 and negative 2. So I'm going to put a plus minus here. And then the square root of 3 is not nice, so I'm going to leave that alone. And then the square root of negative 1, well, that's I. That's imaginary. So all of that is equal to x plus 2. So I just kind of cleaned up that left side. And then the last step I'm going to do is I'm going to subtract this 2 from both sides. And really, I'm just going to stick the 2 in front of the plus minus, the negative 2, sorry. So my final answer will be negative 2 plus or minus 2 times the square root of 3i. And this is equal to x. There's two answers, but it's imaginary. So I'm going to leave that there. Now, we haven't done that for a while, but the method that I used was complete the square. If you did a quadratic, you get the same answer as me, but those are two different ways to do it. So it says, Pauly thinks that all quadratics can be solved by factoring, but we just showed that, especially in B, that it doesn't factor. So is this true? And the answer is no. Some quadratics are not factorable. And the ones that aren't factorable, we have methods that we can choose, and the methods that we choose are complete the square, or we could use the quadratic formula. They both will work. It's just kind of which one do you prefer between those two if it's not factorable. So it says, let's show Pauly how we can use this with polynomials. So it says this polynomial has a factor of x minus 3. So they're telling you already that x minus 3 definitely divides into this big long thing evenly. And it says find all the solutions to this. So I'm going to take this big polynomial and divide it by x minus 3. So I have the x minus 3 has two parts to it. And then this has 1, 2, 3, 4 pieces to it. So I'm going to make a 2 by 4. And on the outside, I'll put my x minus 3. And the last row will be my remainder, and it's always the last row. So the first term that I have is 2x to the third. So I'm going to kind of work backwards here. So to get 2x to the third, x times 2x squared would give me 2x to the third. And then when I multiply that times negative 3, I get negative 6x squared. And I need negative 6x squared, but I already have it. So in this thing, I need nothing else for x squareds. So on top, I'm just going to say plus 0 or times 0 there, and that would give me a 0 here. Let me just make that black, sorry. And then I need negative 100x. So I'm going to put a negative 100x in this part right here. So to get negative 100x, I do x times negative 100. And then negative 100 times negative 3 is positive 300. And that's what I needed at the last part. That's what I have right here. So I have a remainder of 0. I have nothing. So that means that it went in perfectly as it was supposed to. So it says find all the solutions. Well, one of the solutions we actually got just because they told me is a factor, and that's x minus 3. And if you set that equal to 0, or you could just see it, it's going to be x equals 3. So that's one of my answers. And then there's two more answers because this thing is degree 3. This 3 is the highest exponent. And the other two answers are inside this part right here, which I'm going to write this as 2x squared, skip the 0, minus 100, and set that equal to 0. Well, we already did that problem. We did it up here in part A. So I'm going to say x is equal to, and we'll say plus or minus the square root of 50, or if that really bothers you, we can do 5 times the square root of 2. But either one will work because we're going to show you what happens when we look at a graph of this. So it says graph this whole thing, this 2x cubed minus 6x squared minus 100x plus 300. It says how many x-intercepts are there? Does this surprise you? Well, to me right now it looks like I have one answer and then there's two more here, so that's 1 plus these two here, so it should be a total of 3. And that makes sense because it has degree 3. So we're going to graph it anyway just to take a look and see what that looks like. So I'm going to go into Desmos and I'm going to type in that 2x to the third minus 6x squared minus 100x. So we'll open up Desmos. Wait for the thing to go. So I got 2x to the third minus 6x squared minus 100x. Oops. And then plus 300. And if we look here, I got this crazy quadratic. I'll make it a little bit bigger here, or zoom out a little bit. And it turns once on the top and once on the bottom, which makes sense because it should turn, one less than the degree. And then it goes up forever on the right and then down forever on the left. But I'm more interested in what are the x-intercepts. So I'm going to zoom way in here. And one of them is right here at 3, 0, which we already thought. And then I get these other ones, but they're weird decimals. They're the same number, but they're different. The negative 7.07107, and the other one's 7.07. But I have a sneaking suspicion that that's going to be negative the square root of 50, and then the other one's going to be the square root of 50. And that's what those are, actually, right there. And that's why we got those two answers. So if I go back to looking at this right here, how many x-intercepts were there? Well, there was 3. And no, I'm not surprised because, there we go, because the degree is 3. So it says, let's try one more. And it says, let's do this one. And it says x equals negative 1. So in this one, if they say x equals negative 1, that means the factor is going to be x plus 1 in parentheses. So kind of working backwards here. So it says find all the zeros. So I'm going to make a 2, and then this has 1, 2, 3, 4 parts. So 2 by 4. And then this last row will be my remainder. That's always true. So I put x plus 1 on the outside. And then this first term is going to be x cubed. So x times what gives you x cubed? Well, that's got to be x squared. So when I multiply 1 times x squared, I get x squared. But I need 5 of them total, positive 5 of them. So I'm going to put a plus 4x squared to give me 5 total. And I look at it this way. So that'll be plus 4x. And then this will be plus 4x. And I need a total of 20x, so I'm short 16 x's. So then this will be plus 16. And then down here, this will be 16. And then I need 16. I already have it. So my remainder is 0. So I have one of my zeros is going to be negative 1. And then the other zeros are going to be inside of this. But I just take this and set it equal to 0. But again, this looks like the problem we just did. And that's the one that's way up here. And we got this weird answer. We already know what x is going to be from that. It's going to be this weird answer where it has imaginaries in it. So I'm going to write negative 2 plus or minus 2 times the square root of 3i. And it says, how many x-intercepts are there? And then it says, does this surprise you? So we're going to graph it, and we're going to look at this one. Now, imaginaries, there's something about imaginary numbers. They don't actually show up. But we'll take a look, and we're going to see how many x-intercepts there are. So I'm going to type that into Desmos. So I should have x cubed was the original. I think I have to peek back there one more time. X cubed plus 5x squared plus 20x. And the last part was plus 16, sorry. Okay, so I put that in there. And I'm going to go look at what this thing looks like. Now it should turn 2 times is what we're thinking. That looks really weird. And it crosses at negative 1, 0. And that makes sense, but it doesn't cross anywhere else. And I'm trying to see if I zoom way out of it. Looks like anything if it turns. And it doesn't. Let's see if I zoom in better. So it only crosses once that we can see, and the reason why the other ones don't show up is because it's imaginary. So in here, how many x-intercepts are there? Well, technically, there's 3, but 2 are imaginary. And the other one we call is real. And the real one is at negative 1. So that's pretty much the whole thing. There's a check your understanding I'd like you guys to try. Going through the quick notes, I'm going to go put the answer key to that up, and then we'll go through that in class. But you can try to check your understanding for sure. So good luck.